Okay, how about this first one? What do you guys got? How about super simple? Movement, even easier. Not, no. Speed. Literally measuring how fast those molecules are moving, atoms are moving. Okay, so I want to calculate the amount of heat needed to raise the temperature. 250 grams of water. I didn't put it on here, but I just assumed you guys would look it up. And the C, for the specific heat for that, is 1 calorie per gram degrees C.
Science for 52 degrees, which is 0.5.
Oh, jeez. I didn't actually read this whole question.
You don't even need to know how many grams, right? I don't know. I thought that.
I shouldn't have given you this question. That's really what it is. I didn't read it very carefully. I just read the temp change, and I didn't realize the temp change had a... I wasn't thinking it had a phase change. This question is much more involved than what you did, so we're going to skip this one. There's actually 5 different calculations you need to do to calculate this, because stuff happens as I'm changing phases. This next one we can do. The first thing I would probably do just to make it easier on myself is take this and make it 1,200 grams. That way I don't have to worry about any unit conversions. $350 calories to this with an initial temperature. What will the final temperature be? So if you look up the specific heat for copper, it's 0.092 calories per gram degree C. And what I'm looking for in this problem is a temperature change. So I'm going to use the specific heat flipped over to give me a temperature number. I'll put 350 calories in the numerator so that I can cancel out the calories in the denominator. And then I'll put 1,200 grams in the denominator so I can cancel out the gram unit. And then I've got a degree C unit in the numerator. It's, what do we got here? 350 divided by 1,200 divided by 0.092. So 3.2. Is that my answer? No. What is this 3.2? How much the temp went up when I added this 350 calories. So then my answer is going to be 22, just 22? Yeah, 22 degrees C. All right, this one isn't super easy, and we got to think about a couple of things associated with this. So I can't straight away calculate everything that I want for the lead, but I can calculate everything that I need for the water. So I've got this container of water, and I take this chunk of lead and I drop it in here. And the things that we need to realize are the lead goes into the water temperature goes up, so that means the lead was hotter than the water. Why does the water's temperature stop going up?
Because lead equals water.
As soon as the water's temperature and the lead's temperature are equal, I get a stoppage of energy flow. So I actually do know what the lead's final temperature is going to be, because I just determined what the water's final temperature is going to be, and they have to be equal to each other. So knowing that, I can calculate my energy for my water. So I'll use 1 calorie per gram degrees C. And let's see, my change in temperature is 45. And my mass is 300. So this is the amount of energy that the water gained. Where'd the water's energy come from? The lead gave that 13,500 calories to it. So if this is the water's Q, what is the lead's Q? Almost, but opposite. So it's a negative sign. It's the exact same magnitude, but the lead's Q needs to be negative 13,500 calories because it lost 13,500 calories. Okay, and so since I'm trying to find the lead's initial temperature, and I already know the lead's final temperature, what is it going to be? 60. So I need a temp unit. So lead specific heat, I'll just write it upside down. Grams, degrees C, 0.038 calories. So negative 13,500 calories goes here. So that way I can cancel out the calorie unit. And then I need to cancel out the gram unit with 80 grams here. Cancel out the grams, and so I'm left with a degree C. So divided by 0.038 and divided by 80. So 4440 degrees C. Negative. So what is that negative 4,440 degrees C? Change in temperature. So the lead dropped into this water and it was 4,000 degrees and it dropped in and the water basically stole all that energy and then its temperature increased. So something interesting to think about is look at that lead's temperature. It's a ridiculously high number, right? And so how much did the lead's temp change? Over 4,000. And how much did the water's temperature change? 45 degrees. Why?
Because there's far less light.
Water has a really high.
One, there's 4 times, about almost 4 times as much water, but that's not a 4-time change, right? So what's the other problem?
Water has a really high.
Water specific heat is 1, and this guy's is 0.038. So those two things together make the temperature change dramatic, or temperature difference dramatic. So then I have temperature, change in my temperature is temperature final minus temperature initial. And what I know is my change in temperature is negative 4,400 degrees C. And my final temperature is what I'm looking for. And my initial, no, I screwed that up. No, that's right. That's right. I know my final temperature is 60 degrees. And what I don't know is my initial temperature. Okay, so I flip-flop those guys. I get initial temperature over here, and I'm just going to add this to it, and it's going to be 4,500 degrees C. And it looks like 2 sig figs is what I got. So there's my answer. My initial temperature was 4,500 degrees C. Okay, how about this last one? Well, let's start off with what was the energy of the match used for? What was that energy in for? To start those bonds a breaking. And once those bonds start breaking, what do they do after I separate the, since we're talking about a piece of paper, what's the molecule that's actually being burnt? It's glucose, right? Because paper's just wood. So as those glucose molecules break, and we had that up on the board before, right? The glucose plus a couple of oxygens. And put those guys together, those oxygen bond breaks, and the oxygen and the carbon and the hydrogen and the glucose break apart. And that's what this match is used to do. And then what happens? How come it's okay to take the match away?
Because it's
No, you absolutely need to have a heat source to continue that breaking.
It makes its own heat source.
Where's that? That's my question. Where's that come from?
The reaction.
So when the bonds reform, when we switch this, when all of a sudden I start making my CO2, and what's the other part of this? CO2 and what do you get out of respiration? Water. So when you burn the glucose, you initially have to break those bonds, and that's the glucose and the oxygen bonds need to be broken. And when the carbon dioxide and water bonds come back together, then I get a bunch of energy. I get so much energy, basically three things happen. One, I have enough energy to break the next glucose apart. Two, I have enough energy to see it. And I have enough energy to actually feel the heat come off of it. That's it.
So it's number 2.
Number 2, the one that I shouldn't have given you?
Yes.
What about
You said
it?
there were 5 specific